Generative AI is moving beyond static outputs. We are transitioning to autonomous systems that execute multi-step reasoning, real-time reinforcement learning, and interact with digital tools. This creates a direct tension in physical infrastructure. The computational profile required to train a trillion-parameter agent conflicts with the requirements for serving that same agent in real time. Pre-training demands planetary-scale throughput. The primary objective is moving massive datasets across thousands of processors at peak velocity. Serving these models require ultra-low latency. The system must maintain state-dependent computation for continuous interactive loops without stalling. Google resolved this conflict by splitting its 8th-generation infrastructure into two specialized processors, the TPU-8T, engineered for training throughput, and the TPU-8i, built for inference. Silicon-level bifurcation is the mathematical path to computing the next generation of reasoning models at scale. When training trillion-parameter frontier models, the primary bottleneck is often data ingestion delays rather than a lack of raw processing power. The TPU-8T is designed for this scale. It operates in Superpods of 9,600 chips to deliver 121 exaflops of native compute. Google integrated managed Lustre with direct-to-chip remote direct memory access. Massive datasets bypass traditional storage choke points, flowing through dedicated RDMA pipelines. Once data arrives, the TPU eliminates processing overhead, shifting block-scale multiplication directly inside the matrix multiply units, or MXUs. This native MXU quantization allows the chip to run high-quality, low-precision FP4 computation. It balances arithmetic operations with network demands, preventing secondary thread delays. Raw compute density is ineffective if the architecture leaves tensor cores idling, waiting for data blocks. At a scale of 10,000 chips, theoretical peak performance is secondary to system reliability. In clusters this magnitude, single-node failures are a mathematical certainty. Because these chips are tightly synchronized, one failure halts the network.
If a human engineer must manually locate and reset a failed chip, the diagnostic delay lasts at least 30 minutes.
This results in zero throughput for the entire cluster. This creates a distinction between theoretical throughput and operational goodput. Goodput measures the actual forward progress the system makes despite these failures. Google aims to maintain 97% goodput across tens of thousands of chips. Maintaining that progress requires an automated diagnostic system capable of detecting failures at the nanosecond scale. The moment a chip fails, the network must independently identify the fault and dynamically reroute the workload around the dead hardware to maintain operations. Even more difficult to detect is silent data corruption, where a chip quietly miscalculates and infects the entire model state without triggering an error flag. At the frontier of AI research, raw exaflops are only useful if paired with the systems-level fault tolerance necessary to survive continuous hardware failures. Post-training and inference tasks involve the real-time serving of autoregressive decoding and mixture of experts models. The primary constraint on these interactive loops is the latency wall. Mixture of experts models require massive all-to-all communication. In a standard 3D torus mesh, physical data distance creates delays that stall reasoning. For the TPU-8i, Google engineered a hierarchical structure known as the Boardfly Topology. Boardfly collapses the network diameter, drastically reducing the distance data travels between the 1,152 chips within an inference pod. The result? Boardfly reduces all-to-all communication tail latency by up to 50% compared to the torus baseline. For agents executing millions of concurrent requests, the physical speed of data across the network dictates the speed of the model's reasoning. During long context decoding, processor cores often sit idle while waiting on memory retrieval from off-chip storage, a bottleneck known as the memory wall. The TPU-8i addresses this by hosting the key-value cache entirely on the silicon itself. Hosting that cache requires 3 times more on-chip SWAM, packed directly alongside the central compute cores to minimize idle time. Managing this density requires a specialized hardware collectives acceleration engine. This engine yields an additional 5x reduction in on-chip collective latency, ensuring the cores remain active. These memory and network optimizations result in 80% better performance per dollar for low-latency serving, making the mass deployment of agents economically feasible. 25 years ago, the mandate to organize the world's information required Google to invent entirely new data center infrastructure. A willingness to fund high-risk, ground-up hardware bets established the technical foundation for modern data processing. Solving for generalized intelligence today demands that same commitment to custom infrastructure.
That development process is now becoming a virtuous cycle. During the design of the 8th generation TPU, an AI agent named Alpha Evolve was used to optimize the chip's low-level logic circuits. The circuit designs proposed by the AI were counterintuitive, yet proved so efficient they were integrated directly into the physical silicon. This marks a shift where software-driven optimizations are directly refining the hardware that executes them. As agentic computing scales, the role of general-purpose processors is expanding. While TPUs handle dense mathematics, the logic required for planning and tool use places a renewed burden on CPUs. Orchestrating an agent requires managing complex virtual machines, compiling code, running simulation sandboxes, tasks that remain the domain of the CPU. CPUs are required for orchestration, creating digital sandboxes, managing virtual machines, and checking agentic loop results. Effective AI partnership requires an end-to-end hardware stack, where every component, from the CPU to the specialized TPU, is tailored for a specific stage of intelligence.